Nothing beats more videos on continuity. In this one, we're going to talk about properties of continuity. Let's go ahead and take a look here. Alright, first we're just going to look at some initial continuity rules to get us started. Now, here we go. Here's the setup. Assume we got some functions, say f of x and g of x, and we're going to assume they're both continuous at the location x is equal to a, and then moreover, we're going to let c be some real number, and n here be a natural number, one of the counting numbers, 1, 2, 3, 4, and so on. Then each of the following functions are also continuous at x is a. Okay, so backtrack it a little bit. F of x, g of x, both continuous at this location x is a. We got c is just some real constant, and n is a real constant, but it's a whole number that's positive. Then, if that's true, each of these functions right here, as we're going to see, going to be continuous at x is equal to a as well. Assuming, of course, f and g are both continuous at x is a. And that is the sum of the functions f and g, the difference of the functions f and g, the product of the functions f and g, the quotient f of x divided by g of x, assuming, of course, g of x is non-zero, constant times the function, and even the function raised to a whole number power that's positive whole number. Now, just to kind of get a understanding of why that's true, remember we've already established the limit laws. And because if a function f, and in this case g as well, are continuous at the same location x is equal to a, then of course their limits must exist. Right? That's one of the criteria for the functions being defined. Continuous at x is equal to a. Functions got to be defined, the limit must exist, and those two things must be equal to each other. So it's not surprising that all of these properties are true, because these are already properties of limits that we've established, and thus the only difference now is that at this particular limit that exists, it must be equal to the value of the function at that location as well. So we're going to use those properties in this video. Also, some other properties involves continuity of our elementary functions here. And so in this list, A, B, C, D, E, F, not G, we have a variety of families of functions that are all continuous for which they're defined. In fact, that's their domain, right? As long as the function is defined, they will be continuous at the location. Now, some of these families of curves that you see here, you might be thinking, well, they're not defined everywhere. Right? There's definitely locations for which they can be undefined. And that's okay, because we're not saying they're continuous at the places they're undefined. As long as they're defined, they will be continuous. What are these functions? Polynomial functions. Think of all those graphs, right? Those are nice ones, continuous over their domains, and polynomial functions have domains that are all real numbers, so they're always continuous. Rational functions. Now, rational functions can definitely have places for which they're undefined, but as long as they're not undefined, they are defined, the rational function will be continuous at that location. Same goes with trigonometric functions. There's a variety of trigonometric functions that have vertical asymptotes and whatnot. Well, other than those locations for which they're undefined, they're going to be continuous. Logarithms. Logarithms have restrictive domains as well, but on their domains, they are continuous. Exponential functions, of course, are continuous for all real numbers, since that's what their domain is. And finally, power functions. Big realm there, right? Root functions, functions to the whole number power, etc. A lot of different things that can happen there, but as long as they're defined, they're continuous. That's what this list is. And you try to just rationalize that, right? Can you think of an elementary function that is having some type of hole or jump or gap in its graph? Rational functions have holes, but no jumps. All the rest of these functions don't. So really what it comes down to is, as long as you're not piecewise defined, you're one of these elementary functions, then as long as you're defined, you're continuous. Now, what if we have some kind of situation where we have a composite of two functions? Let's say that we have function g of x, and it's continuous at some location x is equal to a. Okay, so g continuous at a. And then you also have a function f of x, and it's continuous at the location g of a. Of course, the result of inputting a into g, and then that output value becomes the input for this function f of g of x, as we see here. And that is, as long as there's continuity as just described, the composite function f of g of x is going to be continuous also at the location x is equal to a. So basically, good things happen, you got continuity. There's some not so good happening at some location, it's possible that you don't have continuity. That's what this is all about. Now, we're going to look at a couple of examples here, and it's supposed to kind of show some of these properties that we just talked about. And in this particular example, we are asked to find a limit. It's this limit right here, of course. As you see, limit is x goes to 2 of the quantity 3 divided by the polynomial 2x to the 5th minus 4x squared minus 50, and then all of that quotient raised to the 4th power. Now, what we see here is a rational function, right? Right in here, rational function, right? But not only that, we have a rational function being raised to the 4th power. And so the entire thing here, all of this, right, that is some composite function like we've described in the previous topic. So you say, okay, what's it really mean? If that inner function, think of that inner function, the rational function is like your g function, as long as that is continuous at x is equal to 2, and then the result of that is some location that is continuous raised to the 4th power, then this entire function that we see that we're taking the limit of is going to be continuous at x is 2. And thus, as long as that is fine, then in order to evaluate the limit, we just evaluate the function there. So let's do that. Let's think of the inner function. Let's call it g of x. All right, let's call it 3 all divided by 2x to the 5th minus 4x squared minus 50, right? And let's think of our f of x as x to the 4th. And so really what we're taking the limit of here is f of g, and the whole point is that f of g of x here is literally that function 3 divided by 2x to the 5th minus 4x squared minus 50 all to the 4th power. I like that 5. Let's make that 5 a little more clean. Yeah, I like that better. That one too. Okay. So then, first check, right? What's up with g of 2? g of 2. Just plug it in. That's 3 all divided by 2 times 2 to the 5th minus 4 times 2 squared minus 50. So as long as we're continuous there, and of course it's a rational function, so part of it was elementary functions are continuous over their domains. One of those families of curves was the rational functions. So as long as this thing is defined, we know we're going to be continuous. And so make sure it's defined there. 3 divided by 2 times 2 to the 5th. All right, what is that? That's 32 minus 4 times 4 minus 50, which gives us a 3 divided by 2 times 32 is 64 minus 16 minus 50. You say, okay, are we defined there? Is that 0? It's not 0 in the denominator, that is. That's 3 over 64 minus 66. So that's just a negative 3/2. So you know what? The inner function, that rational function, g of x as we're calling it here, is defined at x is 2, and it's negative 3/2. And so we know we're going to be continuous for the inner function. Now the outer function, x to the 4th, if I then plug that in, right, what is f of negative 3/2 here? Well, that's just going to be a negative 3/2 quantity to the 4th, which is 81 over 16. And so that function is also continuous because it's a power function at negative 3/2, and thus the limit is equal to 81 over 16 because of the property that we just stated right above this, is that as long as the inner function is continuous at the input value of x and the outer function is continuous at that output, then we are continuous there, which means it has to be equal to the output value of the function, because that is the implication of continuity. So there's one example that's kind of utilizing the properties of continuity of elementary functions and also of composite functions. Now here's another example to wrap this up. Look at this one, g of x. This whole combination right here, this combination of functions, negative 2 times sine of x plus the square root of x squared minus 9 divided by x squared minus 3x minus 4. Our goal is to determine all intervals for which this function is continuous. And so we notice that this function is a combination of elementary functions, right? It's a trigonometric function, that's sine function. We got a root function, but a root, of course, is a power function. And then that power function is a composite function here. So we got both those properties. And then that's divided by x squared minus 3x minus 4. So this entire thing right there is a quotient situation. And so those rules that we mentioned earlier in this video all apply. Combinations of functions, continuous, as long as the original function is continuous. And of course, the original functions here are the variety of different families of curves that are continuous over their domains. So when we see a situation like that, a combination of elementary functions, and we're asked to figure out where it's continuous, what that's really asking us to do is figure out really what the domain of the function is, because as long as you define, you're going to be continuous, guaranteed by these properties. So let's go ahead and just find the domain. So G will be continuous on its domain. All right? So then I say, well, what's the domain of G? What's that equal? Let's figure it out. Well, the different pieces of the puzzle here. Well, first of all, the negative 2 times sine x. Negative 2 times sine x, well, that's never undefined, right? Because it's a sinusoidal function, always defined. So that doesn't play a role in the domain here for this entirety of g of x. Now, then we get to that quotient here. Well, we have square root of x squared minus 9 on top, so that's going to play a role, right? Square root of x squared minus 9, because it's in the numerator, that's going to imply that x squared minus 9 is not negative. It's bigger than or equal to 0. And that's the same thing as saying, well, x squared bigger than or equal to 9 here, which of course is the same as saying that x has to belong to the interval negative infinity to negative 3, closed that is, union with 3 to infinity. Now you could use sign analysis to solve that, or you just draw the graph of it, all that, anything goes. But there you go. That's restrictions on the fact that the radicand can't be negative, otherwise you'd be dealing with complex valued inputs of x, which we're not talking about in this video. Now becomes the x squared minus 3x minus 4. Right, well, that's in the denominator. So that's a polynomial function. It's always defined. So really all we care about is when is that non-zero, right? Because if it was 0, then it's not going to be defined as a function for g. So let's figure out when that is actually equal to 0. And then we'll exclude those values from the domain. So when is this 0? Well, that's a factorable function. That factors to x minus 4 times x plus 1 equal to 0 on the left there. And hence the values of x that makes that denominator equal to 0 is x is 4 and x is negative 1. So thus, x should not be equal to 4 and not be equal to negative 1, because if you were, you would not be defined. And so you combine those restrictions with the other restrictions we just saw right here. And if we can find all the values of x for which that's true, both of those restrictions are satisfied, we would come up with the interval for which g of x is continuous, since that would be also the domain of this function, guaranteed by the previous properties that it's a combination of elementary functions, so it should be continuous over its domain. So to help us get a visualization of what that should be, just draw a little, non-straight number line here. Here's values of x. Here's the values of g that we're looking at. We know that at negative 1, we're undefined right there, right? Because you'd be dividing by 0. We know at negative 3, we're equal to 0. We know at 3 down here, we're also equal to 0. And we know at 4, we're undefined. Just combining those two different variety of partition numbers that we discovered from the restrictions. And so you say, okay, where is everything true simultaneously? Well, we know we have to be coming from this interval down there, negative infinity to negative 3. What about between negative 3 and negative 1? Well, we're all good except this problem spot right here at negative 1, because we know we're undefined. 0 is okay, undefined is not. And say, well, what about from negative 1 to 3? Nothing's going to work there, right? Because we have to be coming from this interval right there. And in fact, that allows us to say there's nothing here that will work either, because we have to be from negative infinity to negative 3, including the negative 3 to begin with. So nothing between negative 3 and negative 1 will work. Nothing between negative 1 and 3 will work. And then we say, okay, well, starting at 3, things start to get nice again, right? So between 3 and 4, we're all good. Can't be equal to 4 because of that restriction right there, but we can be equal to anything after 4. And so this is supposed to show us that the function g of x is continuous on the interval negative infinity to negative 3, including the negative 3, union with, we're continuous at 3 all the way to 4, but we're not continuous at 4, union with 4 to infinity. And so you basically just take the intersection of the sets that are providing restrictions over various different parts of domains of the original function that you have. And then once you take the intersection for which all things are satisfied, you get the interval for which the function is continuous. That's the whole point. So, that's the video. So hopefully it helps you get a decent idea about properties of limits and continuity. And a couple more videos on continuity before we move on to derivatives. So stay tuned. Math and Beats. Later.